Hi everyone, welcome back. So in this video we are going to talk about electrochemistry, and normally this is where I would tell you where to find this in the textbook, but for this one this is really bonus. Our textbook doesn't go into electrochemistry, at least not yet, but really what we're looking at is that electrochemistry is a very useful tool for measuring the thermodynamics of reactions. And so we're going to go into some of the details of this. Now, I know that if you've taken instrumental or biochemistry or inorganic, that parts of electrochemistry have been covered in all of those. And so really what I'm hoping to do here is kind of reiterate some of what electrochemistry is, but really highlight how electrochemistry is super helpful for experimentally finding thermodynamic properties. Okay, so in electrochemistry, what we are doing is we're doing redox reaction, oxidation reduction reactions in a controlled way. And so a lot of the time, in order to measure the properties of a redox reaction, what we need to measure is the electron flow. And so to do that, we have to keep our reduction part of our reaction separated from our oxidation part of our reaction. And so in this example, we're going to label the anode, and this is the chemistry definition of the anode, not the physics definition. The anode is where the oxidation is occurring. And so what's happening on the anode side of this cell is that the zinc solid is being converted into zinc ions, and the electrons from that reaction are going to move through the wire and be provided for the reduction side. And on the reduction side, we are taking our copper 2+ and we are forming copper solid. And ultimately what we are measuring is the potential that is occurring as these electrons flow through the wire. And so on this side, this is the reduction side of the cell, and that is what we call the cathode. And so to figure out the energy that is occurring from the electron flow in this reaction, we would do the energy of the cathode minus the energy of the anode. And these E standards, these are what are known as standard reduction potentials. And these are values that are tabulated. Notice that these are both written as the reduction. And so when we do E cathode minus E anode, really what we are doing is we are flipping the anode reaction so that it becomes the oxidation. And that takes care of the sign. So remember, you can either flip and add, or you can use the formula, not both. And so for this, we get that the standard reduction potential for this entire cell becomes 10.104 volts. So with some math and some relationships that I'm not going to go into, we can find basically the Nernst equation. And the Nernst equation is going to be where delta G of the reaction is equal to negative nu Fe. Nu is the stoichiometry. And this is the basically the number of electrons that move through this reaction. F is a constant. It's Faraday's constant, not unlike the ideal gas constant. It's the constant that is used, that is appropriate for electrochemistry. And then E is the potential or the electromotive force. And so this is the energy of the cell. So really, work is being done. We're moving electrons through this cell. At constant temperature and pressure, the free energy equals the maximum possible non-expansion work. And so really, this VFE, this is W. This is a new type of work. Remember last time we talked about how work is P delta V, where we have to change volume. In this case, we are moving electrons, which is a different type of work. But really, what we are saying here is that at constant temperature and pressure, our delta G is equal to W. And that W is equal to negative nu Fe. And this nu Fe, this is just a fancy compressed way of writing the Nernst equation. And the Nernst equation is the equation that you worked with in biochem, analytical, and inorganic. And now, if we want to do the standard, we'd have to put all our reactants and the products in their standard states. Remember that means for solutions, we are talking about 1 molar solutions. And the challenge with this is not everything is soluble all the way up to 1 molar. And so sometimes we have to know the non-standard conditions because many, many times in this world, we don't work with standard conditions. Okay, so now how does all of this relate to thermochemistry? Let's put it into perspective. So we just defined delta G and delta G star, or delta G naught, in terms of electrochemistry. That's this guy and this guy. And that's what was on the previous page. Now, this delta G equals delta G standard plus RT ln. This is basically K. And this delta G standard plus RTL and K, this is the equation that we've been working with for quite some time. And see, we just defined K in terms of activities instead of concentrations or pressures. And so if we combine these definitions, and do some rearrangement, we can basically find an equation that is going to be our E is equal to E standard minus RT over nu F ln of K. And so now we have potentials related to this equilibrium constant and related to delta G. And so this gives us a lot of power for figuring out our thermodynamic properties. So now let's put some things in terms of derivatives so that we can see how things are changing. So if we think about how delta G responds to temperature, we see that we have to consider how this cell potential responds to temperature. Now, and from that, we can say that the derivative of delta G with respect to temperature is really the negative of delta S. This is one of our transforms. Okay. And so when we have delta S is equal to nu F times the partial of the potential with respect to temperature, we're starting to find that this partial of the potential with respect to temperature is going to be important. And so let's talk about what that would be. So really, we are talking the potential versus temperature. And we are wondering how that changes. Well, it turns out that how that changes is the slope. That is the definition of slope. And so if we need this term experimentally, we can measure this data and we can get this term that we need to be able to come up with our delta S. And this might be one of the experimentally the most straightforward ways to find delta S. And then once we know delta G and delta S, then we can use our good friend delta H equals delta G minus T delta S, and we can find delta H. And so this means that with electrochemistry, we are able to measure all of our thermodynamic properties. And finally, now that we've been talking about entropy since about week 2 of the semester, maybe even week 1, this is the first time that we have provided an experimental method for measuring delta S. And we can do that by measuring how this potential changes with temperature and getting the slope from that.